Hello there, welcome back. We just looked at how to determine the magnetic field from a current in the previous video. So now we're going to look at how we determine the net magnetic field from two currents. Before I even present the problem, let me just talk about the steps whenever you determine the net of something. We've worked with more recently determining the net electric field and net potential, etc. And the process is always the same. So the process steps are always important. And in this case, the process steps will be determine the magnetic field from one current. So we focus on one current at a time. We ignore the other one for now and just focus on one of them. And knowing that magnetic field is a vector will determine its magnitude and direction. Then we will do the same thing for the second current, since there are two currents. Determine B from the second current. Again, magnitude and direction. And once we do that, to get the net magnetic field, we simply add the two magnetic fields that we have determined. So let's call this first one B1, second one B2. So to get the net, we simply add the two. And because these are vectors, we will have to do a vector addition to get the net magnetic field. Those are the process steps. Let's look at how that works for an example. So here it says two long straight wires lie perpendicular to the plane of the screen. Wire 1 lies 5 centimeters to the right of the origin and carries a current of 10 amps coming out of the screen. Before I read farther, let me just draw this. So I've got the origin here. I've got wire 1 that lies perpendicular to the plane of the paper, so I only see the cross section, which is a circle, and it's got a current of 10 amps that are coming out of the screen. So I have to show it as a dot, and this is 10 amps I1, and it's 5 centimeters away from the origin. And then I've got wire 2 is 7 centimeters to the left of the origin, so it's a little bit farther out, so I'm going to show it here. It has a current of 9 amps also coming out of the screen, so once again, I show it as a dot. And here I've got I2 is 9.0 amps, and the distance of that wire from the origin is 7.0 centimeters. Okay, let's follow our process steps. So for wire 1, I will determine B1 first. So B1 would be mu naught I1 over 2 pi R1, and these values are 1.26 times 10 to the negative 6 Tesla meter over amp for the constant, times the current, in this case is 10 amps, divided by 2 pi, and R1 in this case is 0.05 meters. And all the units will cancel, leaving out Tesla. And when you punch this into your calculator, you will get 4.0 times 10 to the negative 5 Tesla. So that's the magnitude of B1. We're not done because magnetic fields are vectors and we got to determine the direction. So if you make a thumbs up kind of symbol with your right hand and then move your right hand to place it at the wire so your fingers can grab the wire, and then have your thumb pointing in the direction of current. So in this case, my thumb is pointing out of the screen while I hold it here in front of this wire. You will have the thumb pointing out and your fingers will be curling that way. So that would be the direction of B1. In this case, it would be counterclockwise around the wire. But we're interested in the direction of B1 at this point at the origin. So at the origin, using the two methods that I presented in the previous video, you will see that it will point straight down. So an arc of a circle going through this point, pointing in the counterclockwise direction. The tangent to that will be pointing straight down. So this will be B1. Next, using the same method, I can figure out B2, mu naught I2 over 2 pi R2, which would be 1.26 times 10 to the negative 6 times 9.0 divided by 2 pi times 0.07 meters. And this will give you 2.6 times 10 to the negative 5 Tesla. And once again, in this wire, the current is also coming out. So the magnetic field direction when you use your first right-hand rule will be counterclockwise around the wire. You place your thumb at the wire pointing out of the screen to match the direction of the current, and your fingers are curling in the direction as shown here for B2. But at the origin, which is where we're interested in the direction of B2, this counterclockwise would be an arc that's going this way. And so the tangent at that point is going to be pointing straight up. And I will draw it as a shorter line to show that it's only 2.6 times 10 to the negative 5 Tesla and not 4.0. So the two vectors I care about are here, B1 pointing straight down, B2 pointing straight up. The net magnetic field is going to be the sum, vector sum of B1 and B2. By the way, let me notate the directions here. So this was down as shown in the figure, and this was up as shown in the figure. By now, you've had a lot of practice with vector addition, so you know that the sum total of these two vectors, with the longer one pointing down and the shorter one pointing up, the net is going to be pointing down. You can also see that geometrically by moving B2 so that its tail is at the tip of B1, and then the B net is going to be this guy from the original origin to the final tip. So we see that those have to be subtracted. So I would have 4.0 times 10 to the negative 5 minus 2.6 times 10 to the negative 5, which will give me 1.4 times 10 to the negative 5 in the down direction as we saw. If you wish, you could have assigned signs to these things. So you could have called B1 negative because it's going down. Once you set that coordinate reference, you can do that. In that case, B2 would be positive. And then when you add them, you'll get a negative number, which will also mean that it's pointing down. So that's the net magnetic field from these two currents. Now let me show you a little bit of a different case with the same numbers. So instead of those wires lying like they were, what if I had B1 still lying where it was, so 5 centimeters to the right of the origin, carrying a 10 amp current, I1. And then I2, instead of lying left of the origin, I'm going to move it above the origin. So it's going to be over here, 9 amp, and let's say it lies 7 centimeters above the origin. And my intent is still the same. I want to figure out the net magnetic field at the origin. All right. The process is exactly the same. The numbers will exactly be the same. So the B1 value from I1 will still be pointing straight down, and it'll be 4.0 times 10 to the negative 5 Tesla. B2, the value will still be the same, 2.6 times 10 to the negative 5 Tesla. But this counterclockwise direction, when it goes through the origin, will now point to the right. So this will be B2, 2.6 times 10 to the negative 5 Tesla. So the process is the same. I still have to add these, but I got to add them as vectors. So now when I move the tail of B2 to the tip of B1, I'll get that. And then for the net magnetic field, you will have this arrow here. This will be B net. And so to determine its magnitude, you will have to use Pythagorean theorem and get the hypotenuse. And to get its direction, you can figure out this angle as arctan of B2, the opposite side, over B1, the adjacent side. You've done a lot of this with other problems, so I'm actually going through this fairly fast. My main point in illustrating this example is to show you that the process steps in both of these cases are identical. These process steps work in any orientation. The process is to determine the magnetic field from one wire first, then the other wire next, and then add them as vectors. So in this case, adding them as vectors meant subtracting the values. In this case, adding them as vectors required Pythagorean theorem and SOHCAHTOA, but the process is the same in both cases. That's the important thing for you to see. All right, to recap, we figured out the net magnetic field from two currents in this example, and we did that by first determining the net magnetic field from one of those currents at the point of interest, and knowing magnetic field is a vector, we figured out its magnitude and direction. And when we did this, we put blinders on and ignored the other current. Next, we did the same thing with the other current, ignoring the first current, determined its magnetic field, magnitude, and direction, and then finally added them as vectors to get the net magnetic field at that point. Thank you.